In this video, we're going to talk about vectors, what exactly vectors are, and some different operations that we can do with them. So let's start right away with a definition. A definition says that a vector in a plane is a line segment with a specified direction. So I'm just going to draw an example from P to Q. This is the vector PQ, which we indicate it's a vector by putting an arrow over the top. P would be called the initial point. Q is the terminal point. And so PQ is the vector going from P to Q, and so the direction that is specified is in the direction from P to Q. Now, the magnitude of this vector is the length of the line segment, and we have special notation for the magnitude. So the magnitude denoted by our vector PQ inside of double absolute value bars is the length of the line segment. And we say that two vectors are equal if they have the same magnitude and the same direction. So in order for two vectors to be considered equal, they need to be the exact same length and they need to be going in the exact same direction. Now, if you imagine I could put a vector, let's just say here's one of our vectors, and I draw another vector that's the exact same length and at that exact same angle. Those would be equal vectors still, because you can just pick one up and put it where the other one is. As long as they have the same length in the same direction, they would be considered equal. And lots of times we denote a vector by a lowercase letter. It's usually in bold if you're looking at a book, but it's hard to write bold with handwriting, so we tend to put the little vector arrow over the top. So if V is equal to the vector AB, then V actually represents the set of all vectors that are equal to vector AB. So let's go ahead and do an example working with vectors. We're going to have an initial point and a terminal point for two different vectors. We're going to determine their magnitude and find out if they're equal to each other. So we'll say that V extends from 0, 0 to 3, 4. And the vector W extends from -2, 3 to -5, -1. First thing we're going to do is find the magnitude of both of these vectors. Well, we know magnitude is the length of that line segment, and all we have is the initial point and the terminal point for both of these line segments that make up our vectors. But we can find the length of that line segment by using our distance formula to find the distance between those 2 points. So I can find my magnitude of vector v by using my distance formula. Remember the distance formula, you get the square root of your change in y's squared plus your change in x's squared. So if I simplify this, I have 4 squared, which is 16, 9 squared, or 3 squared, which is 9, 16 plus 9 is 25. So I have a square root of 25, which is 5. And now I'm going to do the same thing to find the magnitude of vector w. I have my change in the y's, so -1 minus 3 squared plus my change in the x's, -5 minus a -2 squared, all under a square root. So this guy is -4 squared, so that's positive 16. And this would be a -3 squared, so positive 9. 16 plus 9 is again 25. So I also get the magnitude of vector w is 5. So part B, we're going to ask, are these two vectors equal? And it's possible they might be because they have the same magnitude. But in order for them to be equal, we need the same magnitude and the same direction. So part B is vector v equal to vector w. We know they have the same magnitude. To figure out if they have the same direction, I'm just going to roughly sketch what they look like. We said that vector v started from 0, 0 and extended to 3, 4. So this is vector v. And vector w started at -2, positive 3, and then extended to -5, -1. It's going in that direction. So I can see just from sketching them very roughly, they're not equal vectors because vector v is going in this direction up to the right, and vector w is going down to the left. They're going in opposite directions. So no, they are not equal. They have opposite direction. So even though the magnitudes are equal, the vectors themselves are not equal because they're going in opposite directions. All right. Now, if v represents displacement, from point P to Q, and W represents the vector from Q to R, then V plus W represents displacement from P to R. And so what I mean by that is if this is point P, we'll say here's Q and here's R. P to Q is vector V, Q to R is vector W, and then going directly from P to R, that's what's considered vector V plus vector W. So that's the way vector addition works geometrically. We also will learn a way to do it algebraically. Now, if V is multiplied by a real number K, the magnitude of K times V is absolute value of K times the magnitude of v. The direction of kv is the same as the direction of v if k is positive, and opposite of the direction of v if k is negative. So you can think of multiplying by a constant as just lengthening or shortening the vector by a certain factor. But the direction will either stay the same or flip the other direction if you have a negative value. So this kv is called a scalar multiple of the vector v. kv is a scalar multiple of vector v. If k happens to equal 0, then k times v equals the 0 vector. And the 0 vector has magnitude 0 and no direction. You can think of it as not really going anywhere, and it has no length. Now, this is all thinking pretty much geometrically, and now we're going to learn how to think about vectors more algebraically. Let's suppose vector v is the vector from P to Q, and the horizontal displacement from P to Q is A units, and the vertical displacement is B units. Then we can represent the vector v in something called its component form. And it looks like little angular brackets, A, comma, B. And again, that's called the component form of vector v. So when you have it in those angular brackets like that, the first piece is your horizontal displacement, and then the second piece is your vertical displacement. And this describes the way the vector is moving from the initial point to the terminal point. So if we are to sketch a vector with its initial point at 0, 0, then we say it's in standard position. So sketching a vector with its initial position at 0, 0 of the rectangular coordinate system. Is called standard position. So for example, let me just draw a vector in standard position. Here's my x and y axis. I'm putting its initial position at the origin. And we'll say there's A, there's B. So this guy is vector AB in component form. So showing us the horizontal displacement and the vertical displacement. All right, let's do an example using all of this information that we've just taken in. Let's suppose that vector v has initial point -4, 5, and terminal point -1, 12. First thing we're going to do is find the component form of v. So let's just do that before I even write down what part v is. So the component form, remember, we need to find the horizontal displacement and the vertical displacement. Let's start with the horizontal displacement. The horizontal displacement is the change in our horizontal position. So I end up at -1 for my x, and I started at -4. So my displacement is the change in my x's, -1 minus -4, which is 3. And then my vertical displacement is the change in the y's, 12 minus 5, which is 7. So this tells me that vector v in component form is 3, 7. Now part B, we're going to pick up our vector and move it to a different starting position. So if vector v is placed with initial point -2, -4, what is the terminal point? Well, we know the vector is now starting at -2, -4. And I know the component form of my vector, 3, 7, meaning my horizontal displacement will be 3 and my vertical displacement will be 7. So I can find my terminal point by taking my x-coordinate, which was -2, and adding to that my horizontal displacement of 3 to get 1. And my y-coordinate of my terminal point will be where I started, -4, plus my vertical displacement, which was 7, and I get 3. And so this tells me my terminal point is the point 1, 3. So that just shows you how you can pick vectors up and move them around. They'll change initial points and terminal points, but they'll keep the same magnitude and the same direction. And writing it in component form helps describe what's going on in those situations. Now, another nice thing about this component form is figuring out if two vectors are equal when they're written in component form. So two vectors, we already said two vectors are equal if they have the same magnitude and direction. But two vectors are also equal if and only if their components are equal. And that means if V is A1, B1, and W is A2, B2, then V equals W if and only if A1 equals A2 and B1 equals B2. So their components have to be equal in order for them to be equal vectors. So now that we know the component form, we can talk about a lot of different operations on vectors and write down what those operations mean in an easy to understand way. So here's a bunch of operations for our vectors. We're going to say V is A1, B1, and W is A2, B2. Then V plus W is A1 plus A2, B1 plus B2. So you just add the components when you're adding the vectors. Similarly, V minus W would be A1 minus A2, B1 minus B2. So you just subtract component-wise. And lastly, a scalar multiple of a vector is just the same thing as multiplying each of the components by that scalar. So K times V is KA1, KB1. So let's do an example using a couple different vectors. So for vector R, which equals negative 3, 10, and vector S, which is 12, negative 7, let's find, we're going to start with R plus S. Well, we know now that when we have component forms for our vectors, we can figure out what the sum of the vectors is by adding the corresponding components. So R plus S is going to be equal to negative 3 plus 12 for the first component, and 10 plus a negative 7 for the second component. If I simplify this, I get 9, 3 for my R plus S. Then part B, let's find S minus R. But again, we just do that component-wise. So I would take my vector component for S, I have 12 first, and then minus negative 3, and then I'm going to have negative 7 minus 10. That's going to give me S minus R. So if I simplify this, 12 minus a negative 3 is 15. Negative 7 minus 10 is negative 17. And so I get S minus R is 15, negative 17. Let's do another example similar to that. So for vector A, which is 11, negative 7, and vector B, which is negative 4, negative 6, let's find 6A. So that's a scalar multiple of vector A. But we now know that I can find that by taking that scalar and multiplying it by each of my components. So the vector 6A is going to be 66 and negative 42. And then an example that combines all of this stuff together. Let's find negative 3A plus 10B. Well, first let's find what negative 3A is and what negative 10B is. Negative 3A is going to be negative 3 times 11 and negative 3 times negative 7. And 10B is going to be 10 times negative 4 and 10 times negative 6. So when I simplify that, I have negative 33, positive 21, plus negative 40, negative 60. Now I can add component-wise, so I get negative 33 plus a negative 40, and 21 plus a negative 60 fully simplified, that gets me negative 73 and negative 39. And that is equal to my negative 3 times A plus 10 times B. All right, so now we're ready to learn a lot of properties of vectors. And luckily, the properties of vectors are about what you would expect based on things you know about real numbers. Properties of vectors. And I'm going to have C and D are scalars in all these properties that I'm about to write. First property, vector V plus vector W is equal to vector W plus vector V. So our addition is commutative, that you can change the order that you're adding. Property 2, vector V plus vector W plus vector U is the same thing as vector V plus vector W plus vector U in parentheses. This says that our addition is associative. Property 3, vector V plus the 0 vector is the same thing as just vector V, like you would expect. Property 4, vector V plus a negative 1 times vector V is equal to the 0 vector. So you can think of this as we have an additive identity and we have additive inverses for our vectors. Now we have property 5, all the way through property 11. We have lots of properties. So property 5, C times vector V plus vector W is equal to C times vector V plus C times vector W. So you can distribute scalars. Property 6, C plus D in parentheses times vector V is equal to C times vector V plus D times vector V. So it's another form of distribution. Property 7, C times D times vector V is the same thing as C times D times vector V. So our multiplication of scalars, it does not matter if you multiply the scalars first or multiply one scalar at a time. Property 8, 1 times vector V is just vector V, a multiplicative identity. 9, 0 times vector V is the 0 vector. And just 2 more properties. A scalar times the 0 vector is equal to the 0 vector. And lastly, the magnitude of C times vector V is the absolute value of C times the magnitude of V, which we already knew that property from earlier. Now, a definition. A vector with magnitude 1 is called a unit vector. Then, if V is the vector AB, we can find a unit vector in the same direction of V. So V is vector AB. Then a unit vector, U sub V, in the direction of V is given by U sub V equals 1 over the magnitude of V times vector V, which we can rewrite that a little bit as its component form, A divided by the magnitude of V and B divided by the magnitude of V. So this will get us a vector in the same direction as vector V, but with magnitude equal to 1. So let's do an example where we find a unit vector. Find a unit vector in the direction of 5, -1. Well, to find a unit vector in that direction, I need to find the magnitude of that vector. Once I have the magnitude, I can just divide the components by that magnitude, and I'll have my unit vector. So the magnitude of vector 5, -1, I can get using my distance formula in a way. Remember, your distance formula was the change in the x's and the change in the y's squared underneath the square root. And I know my horizontal change is 5 and my vertical change is -1. So I have 5 squared plus -1 squared, and that will get me my magnitude, which is the square root of 26. So our unit vector is 5 over the square root of 26 and -1 over the square root of 26. It's the same direction, but now it's going to have magnitude equal to 1. Now, there are two very important unit vectors that we care about more than all of the other unit vectors. And they have special names. They're called I and J. So, two important unit vectors are I, which is 1, 0, and J, which is 0, 1. So those are the unit vectors that go in the direction of the positive x-axis and the positive y-axis. Now, these are very important because any vector can be represented as a linear combination of I and J. So a vector V, which is equal to AB in component form, we can also write that as A times the vector 1, 0 plus B times the vector 0, 1. So that is A times I plus B times J. So once you have the component form of any vector, you can write it as a sum of combinations of vectors I and J. So an example of this. Write 12, -1 in terms of I and j? Well, luckily, it's as simple as just taking your first component multiplied by vector I plus your second component, so minus 1 times vector j. And of course, we don't really need to write the 1 there, so you can just say 12i minus j, and that is the same vector, just written in terms of I and j. Let's do another one that's a little bit more involved. Given vector A is negative 9.4 I plus 7.1 j, and B, which is negative 0.6 I plus 3.2 j, let's write negative 2a minus 4b in terms of I and j. Well, let's just go ahead and get started. Negative 2 times a would be negative 2 times negative 9.4 I plus 7.1 j. And then I have minus 4b, and b was negative 0.6 I plus 3.2 j. So now let's just distribute. And that gets me 18.8 I minus 14.2 j plus 2.4 I minus 12.8 j. And then I can just combine my i's together and combine my j's together, and we'll have the fully simplified answer. So this gets me 21.2 I and minus 27 j. And that's the same thing as our negative 2a minus 4b, but written in terms of I and j. So now let's let vector v equal ab be a vector in standard position. And let's let theta be an angle in between 0 and 360 degrees. And let's let that be the direction of vector v, measured counterclockwise from the positive x-axis. So I'm going to draw a picture that describes exactly what I wrote down here, and we're going to learn how to express our magnitude and direction in terms of our angles, and find all sorts of different ways of writing this involving our trigonometric functions. So here is my vector AB. In standard position, and here's angle theta. Then the magnitude of vector v, which we already know is the square root of a squared plus b squared. That's our magnitude. And if we use tangent of theta, we would get b over a. That helps us get the direction of our vector. So I can solve tangent theta equals b over a for theta, and that will tell me that angle that gives me the direction of my vector v. I also have, using trigonometry, that a is equal to the magnitude of v times cosine of theta, and b equals the magnitude of v times sine of theta. And that means I can write my vector v in many different ways. We already had vector v equals ab. This is now equal to magnitude of v times cosine theta, magnitude of v times sine theta. Or if I write it in terms of I and j, v is ai plus bj, which is equal to magnitude of v cosine of theta I plus magnitude of v sine theta times j. So these are all different ways that we can write our vector v. And now we're just going to finish up with a few examples using word problems, really, to get all of our vectors figured out and using all these different ways with the angles. That was a very bad way of explaining it. But basically, we're going to take all this info we just learned in order to solve word problems so that we can see some applications of vectors. So an example. A man exerts a force of 80 pounds on an object by pulling a rope. And he's pulling this rope at an angle of 30 degrees from the horizontal. We are going to write the force vector F in terms of I and j. All right, so I want to write my force vector F. So first thing I'm going to do, let me just draw a quick little picture giving us an idea of what's going on. I have an angle of 30 degrees. We're pulling the rope at that angle, and my force vector is going in that direction. Now, I know my force is 80 pounds. That's going to be the magnitude of my force vector. So we already know the magnitude is 80 pounds. So magnitude of F is 80 pounds. And so if I use one of my versions of writing a vector, the force vector is going to be equal to the magnitude of F cosine of theta times I plus my magnitude of F sine theta times j. Well, this tells me that I'm going to have 80 times cosine of my angle, which was 30 degrees, times I, plus 80 times sine of that 30 degrees, times j. Now, cosine of 30 degrees, we should know that from our unit circle. It's square root of 3 over 2. So this simplifies to 40 times square root of 3i. Plus, sine of 30 degrees is 1/2, so I get just 40j. And there is my force vector in terms of I and j, using just the info they gave us, which was the magnitude, the 80 pounds, and we had our angle of direction. Let's do another example. A ball is thrown from a height of 1 meter. At release, the velocity of the ball is V equals 27.2 I plus 12.7 J, where each component is in meters per second. Find the initial velocity V0 and the angle theta above the horizontal in degrees at which the ball was thrown. And we're going to round it to 1 decimal place. So first, how do we find the initial velocity? Well, your initial velocity is actually equal to the magnitude of the velocity vector. So I can find my initial velocity v0 by finding the magnitude of my vector v. So v0 is the magnitude of vector v, which would then be the square root of 27.2 squared plus 12.7 squared, which is approximately, to 1 decimal place, 30.0 meters per second. And then to find this angle theta, since tangent of theta is b over a, that means that theta will be tangent inverse of b over a. And if I just fill in what my b and my a are, I have 12.7 over 27.2. Type it in your calculator, and to 1 decimal place, it's approximately 25.0 degrees. All right, we have just 2 examples to finish up this intro to vectors video. So this next example, if the magnitude of F1 is 32 pounds, the magnitude of F2 is 24 pounds, and the magnitude of F3 is 15 pounds. Write the resultant force, R, in terms of I and J. So I'm going to be drawing a picture that's going to show our force vectors F1, F2, and F3 and their appropriate angles. I don't have room to draw it right this second, so I'm just going to explain right here. The resultant force is the total force on an object, so it's all of the forces added together. So basically, we need to find a way to write all of our forces, F1, F2, and F3, in terms of I and J, and then add them all together to get our vector R. So let me draw the picture that comes with this problem. I have, here's an angle of 40 degrees below the horizontal. That's F3. F1 is pointing straight up. Then I have an angle over here, 68 degrees, and that's F2. So let's start with F1. The angle for F1 is 90 degrees, measured counterclockwise from my positive x-axis. So that means that F1 is equal to its magnitude times cosine of the angle times I, plus the magnitude times sine of the angle times j. So that's just using the formula that a vector is equal to its magnitude times cosine of theta I and magnitude sine of theta j. So now I can just simplify this. F1 is equal to just 32j because cosine of 90 is 0 and sine of 90 is 1. I'm going to do the same things for F2 and F3. Notice that for F2, the angle that I want is actually 90 degrees plus 68 degrees. So it's 158 degrees. And for my angle F3, I'm actually going almost all the way around. It's 360 minus 40 degrees, so 320 degrees for that angle. So my F2, we said the angle was 158 degrees. So that means that F2 is equal to its magnitude times cosine of 158 degrees I plus its magnitude sine of 158 degrees j. And I'm not going to simplify it further than that right now because I don't have an exact value for cosine and sine of 158 degrees. It's not on my unit circle. Now doing F3, same idea. My angle is 320 degrees. So that means that F3 is equal to its magnitude, which was 15, cosine of 320 degrees I, plus 15 sine of 320 degrees j. And now I can get my resultant force R by adding these three forces together. So we had R is equal to F1 plus F2 plus F3. And since I want it in terms of I and j, I'm going to first group all the things with I together and all the things with j together. So everything multiplied by I was 24 cosine of 158 degrees plus 15 cosine of 320 degrees. That's all multiplied by I, plus everything that's multiplied by j. 32, 24 sine of 158 degrees, and 15 sine of 320 degrees. All of that times j. Now that's the exact answer, but if I round it to just a couple decimal places, I'm going to get negative 10.76i plus 31.35 j as my resulting force. So you can find the resulting force just by adding all of the forces together. Now, if this resulting force happened to equal 0, that would be when we say that our object is in static equilibrium. So if you see something describing static equilibrium, that means all of the forces added together result in a zero vector. Let's do an example where we have static equilibrium. So 2 cranes support a 2,000-pound weight in static equilibrium, as shown in the diagram. Find the magnitudes of T1 and T2. So now let me get us the picture for this problem. Here's T1 with an angle of 45 degrees. And then way over here at an angle of 120 degrees, I get T2, and I have my weight W, which is negative 2,000 times J, because J would be going vertically straight up, and negative 2,000 is the weight pulling it down. And so I want this to be in static equilibrium, meaning the sum of all 3 forces should equal 0. So we know that T1 plus T2 plus W is going to be equal to 0. Now I don't know much about T1 or T2, but I know their angles, and I know then that T1 should be equal to the magnitude of T1 times cosine of 45 degrees times I, plus the magnitude of T1 sine of 45 degrees times J. All of that is T1. And then I can do the same thing with my T2. So I'm going to add to that T2, which is magnitude T2 cosine of 120 degrees I plus magnitude of T2 sine of 120 degrees J. And then I can still add to that my W, which was negative 2,000 J. All of this needs to equal 0I plus 0J, because it's all supposed to equal 0. Well, the only way that these are going to be equal is if all of the things multiplied by I end up adding up to 0, and all the things that are multiplied by J add up to 0. So I'm going to actually set up a system of equations. So equating all of what we get from that, I know that my magnitude of T1 times, it was a cosine of 45 degrees, that was square root of 2 over 2, plus my magnitude of T2 times a cosine of 120 degrees, which was negative 1/2, that has to equal 0, and magnitude of T1 times my sine of 45 degrees, which is also square root of 2 over 2, plus my magnitude of T2 times sine of 120 degrees, which is square root 3 over 2, minus my 2,000 is also equal to 0. That was what I got from the J components. So now I just have to solve this system of equations. And to make everything look a little bit easier, I'm going to go ahead and multiply everything in these equations by 2. I'm also going to move this 2,000 over to the right side. So my first equation, when I multiply everything by 2, I get a square root of 2 times magnitude T1 minus the magnitude of T2 equals 0. And I'm going to add 2,000 to the other side of this equation and then multiply everything by 2. So I get a square root 2 magnitude T1 plus a square root 3 magnitude T2 equals 4,000. And now I have this system of equations here. And I'm going to solve it using substitution. Or no, not substitution. I think I'll do elimination instead. So for doing elimination, I'm going to multiply my first equation by -1. That just changes my signs. And now if I add the two equations together, the T1s disappear completely. And I will get 1 plus a square root of 3 times the magnitude of T2 is equal to 4,000. So that means my magnitude of T2 is equal to 4,000 divided by 1 plus the square root of 3. And this is approximately 1,464 pounds. Now I can take that and plug it back into this first equation to get my magnitude of T2 or T1. So I have square root of 2 times magnitude of T1 minus my 1464 is equal to 0. And this tells me that T1, magnitude of T1, is equal to 1464 over the square root of 2, which is approximately 1,035 pounds. And so we found magnitudes by setting up what looked like a pretty terrible system of equations, but it really wasn't that bad once you get all of the components set equal to each other. So that's all I have for you today on vectors. In the next video, we're going to learn more about vectors, where we learn something called the dot product, which is one of the ways of multiplying vectors together. If you have any questions, feel free to drop them below. If you're a current student, you can also ask in class, in office hours, or in email. And I'll see you guys next time.